All right, we're back with condensation polymers. What's most important about condensation polymers is to think that when you're condensing, that's a physical change in our chapter 1. But right now, what we need to think about is you're going to be condensing something like water or HCl. When you're condensing these molecules, that means you're producing them. That's different than addition polymers in our previous section. Addition polymers in our previous section, they add to themselves over and over and over again until there's no molecules left. Here, typically, we have two molecules, whether it's amines and carboxylic acids to make amides. So you put these two together, you get that one. Or it's alcohols and carboxylic acids, and you make esters. No different than before. When you make one, it's not a big deal, but when you make hundreds of thousands, now we say polyamide or polyester. And these are very common for clothing fabrics in particular, whether it's pantyhose for polyamides like nylon or the polyester spandex kinds of things for the non-wick sports type clothing that you see a lot of athletes and stuff wear because they don't absorb all that moisture. So as we look at nylon, which is one of the most common and the one that we make in class for one of our labs over this chapter, nylon uses a carboxylic acid. This one's actually a carboxylic acid chloride, just meaning instead of an OH it has a Cl. That's a more reactive group. But what's good about this one is instead of producing water, which can interfere with the reaction and slow it down, you're producing hydrogen chloride gas, so you're condensing that molecule instead, and that one's going to bubble up into the atmosphere away from our solution where our molecules are polymerizing together. If this were the case with water, we'd be producing water, which would be adding to the water layer of our reaction and to some small degree slowing it down. So this one works a little bit faster, especially for lab purposes. We want it to happen in minutes, not hours, and HCl can allow for that. We call it nylon 6,6 because there's 6 carbons in both groups. So those numbers in this case are just representative of the type of nylon that we're making. So what's unique here is that you have adipic acid, which has 1, 4 more, which is 5, and then 6. So there's your 6. And then over here you might see it a little bit easier. It says hex because of the 6 in the middle. So that's where they get that nylon 6,6 naming. So just pay attention for those hex prefixes when you get to that matching section. Although condensation polymers do have 2 units that make their polymer not the one of addition polymers. That makes it a little bit easier too. The polymer name here again, this is used to make things like rope. So nylon rope is pretty common for, say, fishing applications when you're throwing an anchor to the bottom of the lake and having to pull it back up. It was also used by Remington to make their synthetic gun stocks back in the I think early 80s and so forth. And then it also makes clothing similar to like the pantyhose that's leg coverings and nylon stockings and so forth for blood pressure kinds of issues as well. The reason that nylon is relatively strong, you may not think of it as strong in the sense of pantyhose because it's very thin in those applications, but in an anchor rope it's very strong enough to pull up really heavy anchors and that kind of thing. Tow ropes between automobiles, sometimes made out of nylon. And the reason it's so strong is we're using polar atoms to attract polar atoms. That's a big feature of our chapter coming up. Because of the dipole on the carbonyl and because of the dipole on these nitrogens, you have a negative feeling atom attracting a positive feeling atom. And this is called hydrogen bonding when it happens between an NH. So hydrogen bonding is very important in the sense that it's the strongest attraction that non-metals can have because it chooses the 3 most electronegative atoms, nitrogen, oxygen, and fluorine, and it attaches them to the least electronegative non-metal, and that's hydrogen. So notice here's that NH bond of the amide, just like it is down here. And those can attract each other through the chain. So because this hydrogen's very electropositive, this oxygen's very electronegative, they can have an attraction between them. So in order to break nylon, in order to break a hydrogen bond. Hydrogen bond is not a real bond, it's just an attraction between these molecules here, these molecules here. Those have to be broken in order for nylon to rip or nylon to, be damaged. So those are the glued forces, those are the intermolecular forces that hold them together. And we'll see a lot about that in our next chapter next week. And then we get to our esters. Esters are using alcohols now instead of amines. Polyester being one of probably the most widely used fabrics for clothing other than cotton. Cotton being a carbohydrate really, just based on its alcohol structure, and we'll see that in an upcoming section of this chapter. But in this case we can produce water or acids, either one. So the HCl or the H2O could be our byproduct in these reactions. So again, we're not using every single atom because we're not adding them together. We're putting two molecules together and then allowing water to leave, or in some cases HCl to leave. In this case we have water between the molecules of the acid and the alcohol as well. We'll show that separately here in a minute. The most common plastic from polyester is called peat. Peat is polyethylene terephthalate, and this is what's used in all soda bottles and water bottles, and can be used in a lot of clothing as well, if it's used as a fabric and not as a kind of formed integrated plastic in some kind of a mold. But what's unique about it is it's mostly nonpolar because of its aromatic ring. So that big hexagon in the middle with 3 double bonds is going to be big and nonpolar. And if it's big and nonpolar, it's not going to be very attracted to water at all. This will allow water to leave because we've lost all of the OHs and NHs that make it superpolar. We still have a couple carbon-oxygen bonds that are weakly polar, but not enough for water to be attracted very well. And this allows water to escape, water to wick from this kind of material. So real quick, let's show you kind of a summary of what we just mentioned, because functional groups will be important specifically for these condensation polymers. So you can imagine that if we have a amine, amines are RNH2. I'm going to write out the hydrogen separate so it's a little bit easier to see what's going on. And then if you add that to a carboxylic acid, here we have an amine, here we have a carboxylic acid, and what you'll notice is right in the middle is 2 H's and an O. So here's your condensation of H2O. These two pieces will come together and make a new molecule. And now it'll be RNH2, lost its H to water. It'll be this carbonyl OH, now lost its OH to water, and just be a carbonyl left. And now what we have is a amide. So amines and acids make amides, and specifically when we make lots and lots of amides in a row in a polymer, because these are just two monomers, we would call that a polyamide. And this is things like nylon that we'll make in class. Slightly different for alcohols. So if you have an alcohol, and you have a carboxylic acid, so carboxylic acid over here again. Notice in the middle you have 2 H's and an O, just like over there, so this is going to be lost as water. The other remaining pieces are going to now be bonded together in order to make what now looks like an RO carbonyl R, which we call an ester. Making one ester not a big deal, but making tens of thousands, hundreds of thousands of esters in a row allows us to make polyester. And that's one that's very common in life for both drinking containers and for clothing. The most important feature of what we're showing here, though, is polarity, because that's something that kind of never goes away. We do have a little bit of a dipole here, a little bit of a dipole there, same kind of dipoles here and there, but most importantly, over here we have that NH. That's the superpolar that can allow for hydrogen bonding, and esters do not have it. So just like cotton that has OHs, polyamides have NHs, and they're going to attract moisture much more so than polyesters, because in polyester these R groups are typically big and nonpolar, and those actually have no attraction to water whatsoever. So what little polarity the ester group has in the middle is overwhelmed by the R groups, and this allows the moisture to wick away or evaporate, cooling the athlete that's wearing those polyester jerseys or whatever, rather than a polyamide if you were to wear a nylon shirt or a cotton shirt. These little NHs and OHs, they would be attracting water because water molecules are superpolar. Their oxygens are very negative, these hydrogens are very positive, and they're going to attract each other, and that's hydrogen bonding. So it's very important to still realize that polarity plays a huge role in the case of these molecules. One thing that we're going to see in our next little section is that polyamides, another name for those, are called peptides. And we're going to see that with proteins. So polyamides come from amino, which is amine, and acids. And we'll see that coming up very quickly in our next section. So we'll see you then.